Dr. Cohen
Okay, let me
knocked down.
test share screen.
Yeah.
Okay, I can share screen. Let me share the preview.
Good morning.
Good
Hey,
morning,
morning.
Dr. Cohen.
Can you see the PDF?
Yeah, I saw the PDF. Maybe you should maximize
Yes.
the page. Okay, it's good.
It works, right?
Yeah.
Yeah. Okay.
Dr. Cohen is on, and he's my colleague. Dr.
Okay.
Cohen is a professor from
That's
I'll
Cornell.
be
fine.
right back. I got to get my coffee. There's 3 minutes to go.
Okay.
Be right there.
So Dr.
I have
Cohen
my
is
copy.
working on topology, and when I introducing Professor Chen, he saw that you have the experience working on topology and finite element secure calculus. So he said your talk might be very interesting. So he logged on.
Yeah, I actually I got my master degree in topology, studying those lots and the Jones polynomial.
So after his retirement, he came to our university, and he had many excellent publications in annals and in Western math. We also have other faculty members, but because these days are holidays, so many of them cannot really attend. So now we have more participants. I think mainly from China. I shared the link in WeChat, but some of them told me they cannot attend. Kai Zhang from Jini University told me he cannot attend it because the restriction. Anyway, I have record this video. Let me wait another 2 minutes. Okay. Let me start the introduction. So it's my honor to introduce Dr. Nong Chen from UCI, UC Irvine, to deliver talk. Before his presentation, let me briefly introduce Dr. Chen's research profile. Dr. Chen got his Bachelor of Science from Nanjing University in 1993, then master degree from Beijing University in 2000. And then he came to Penn State University working on computational math with Dr. Jin Xiaoxu. So during his master study, he's actually working on topology with pure math. So after obtaining his PhD, he did postdoc at University of Maryland, College Park, and also University of California, San Diego. And then he studied a tenure track, a system operation in 2007. And he was promoted to a full professor in 2015. Dr. Chen's research mainly working on finite element method. He developed many efficient algorithms for different types of partial differential equation, including Boltzmann equation, elliptic equation, Maxwell equation, saddle point problems like Stokes problem, like linear elasticity, and he had essential contribution in, for example, in mesh generation, finite element exterior calculus, efficient algorithms, including preconditioning technique, and multigrid algorithms, and other high order or non-conforming weak gauging virtual element construction and the corresponding approximation theory. Recently, he started research on machine learning. So today, he's going to talk efficient transformer, where he decompose near field and the far field attention. That is the title of his talk. It's mainly based on fast multiple method. So let's welcome Dr. Chen to deliver his talk.
Thank you for the invitation and for the introduction. So it's my pleasure to share some of my recent research with you. So this is the most part of this talk. The work is joint work with those the 10 band, those postdoc students, and Professor Stanley Osher and Bao Wang. Before I talk about our work, I promise to give some introduction, some background. Very okay. Why? Wait. Yeah. Okay. Yeah. No. So yeah. So I give some background on this deep learning. A very quick introduction. So deep neural network. This is the first part. So the machine learning. Okay. What is machine learning is doing? Okay. So this is a very simple, okay, again, it's mathematically may not be very precise, but it gives you some, maybe a global picture so you can see what is the machine learning. So this is just a picture, a cartoon. This is the f, the little f, this is a function. We'll use the two. So this is a mapping from capital X to Y. Now you can think of capital X and Y are just the spaces, okay, bar space, Hilbert space. So this is a mapping, okay, denoted by little f. So machine learning is simply replace this function. The function unit is unknown. You don't know the function. You approximate or replace the function by some network, okay. So that's the machine learning, okay, in a rough sense, okay. Now, this circle, those network architecture is going to be very different for different functions. So we have so many choices. So let's go through some typical examples. So the mapping, okay. So why we need those mapping? So this is an example took from the example of Tiffany. You don't have to know the software. So this is a bunch of data. Actually, is for this. Each data represent a number from 0 to 9. So if you find this computer similarity matrix, find this PCA, the first two components, and plot in this picture, you will see those data are mixed together. But if you use the software, they will compute a nonlinear mapping. After the nonlinear mapping, you can think this is the previous is X, this is Y. So after this mapping, then you separate it, you see? So this that's a 10 category. In this after the nonlinear mapping is separated, you can easily recognize those numbers. Okay, so this is one example. So this is another example. So if you look at those data in the 2D, there's a two-dimensional data. It may not be easily separate. Well, I want to now this is the job is to separate data. You can just simply think about the numbers. Now, if the in the 2D in the on the left, this is very hard to draw a line to look at this in two categories. But you can map to the high dimension space, and then just using a linear. This is called this is a plane to separate those two data. Okay, so this is in general a philosophy. So you map the data to high dimension. Now let's look at a simple example. How do you separate? This is actually very easy. If you look at this data, if you look at a coordinate only, that in 2D, right? In 2D, they might be mixed together, but they have a future. This is the terminology called a future. Now here, you can just think about it. The future is color. One is red, one is green. Okay, so if you add the future as an additional dimension, now in the 2D, now the third dimension, I'm going to use the color as coordinate. The red is 0, the z direction is 0, the green is 1, for example. Then in the 3 dimensions, they're separated. Because you're adding the future as an additional dimension, you mapping the data into a high dimension space. This is a very simple example, but it give you the philosophy, okay? So how do you find the mapping? In general, how do you find the mapping? That the previous one is simple. That's you have the future is like a color. You just using that one. You can easily find the mapping. Now the deep neural network tells you, you give me the data, you follow this network, I'm going to find the mapping, nonlinear mapping. Okay, so this is a architecture for this one typical example for deep neural network. It's also called FMN, forward neural network, or fully connected neural network. Now here's some math. So it's also very simple. This mapping, if in the neural deep neural network, is a composition of a fine map plus this activation, nonlinear activation function. So the capital T is just a fine map, or you can think about linear map. W, capital W is a matrix, X is a vector. Matrix times vector, this is linear transformation. This is the simplest one, okay? This mapping is very simple. You cross B, B is called a bias. We will see, so that's like the, when you give the grade to students, you put a 60 as your bias, okay? If you pass 60 is pass, right? Below that is fail, okay? So usually after the transformation, you put a bias there. And that's a very important thing. It's called the activation function. Sigma is called activation function. Without activation function, this is just a linear map, okay, essentially. Okay, mathematically called affine. Affine is a linear process constant. But you compose by an activation function, it becomes nonlinear, okay? So this is nonlinear structure. The combination of nonlinear mappings will give you a very rich this representation or approximation of some mapping. So it's just a simply combination of a linear map and then activation, and then linear map, and then activation. So that's the deep neural network. That's the showing in this picture. So the activation function, the left is called the sigmoid function. That's the traditional one. In the beginning, use that one. But afterwards, this is more popular. It's called the ReLU. Okay, it's just a piecewise linear. But that is very simple, right? It's just 0 or x. Okay. But that's also already nonlinear. Okay, the combination of this simple nonlinear piecewise linear function will give you very rich structure. Okay, that's also a lot of research going on here. And Jingcao Xu, the professor Jingcao Xu, has done a lot of this work to explore the approximation property of this very simple this ReLU, even this network, because of the combination, because of this this optimization we're going to talk about. Okay, that's called the activation function. And again, so you put a bias, it's like you can think about you are giving a grade to students. You have to pass some baseline like a 60, and then you give grade according to the scores, right? So that's the simple example. Now let's look at a concrete example. This is the previous one I mentioned. You have 10 digits from 0 to 9. Okay, so each one is a 28 by 28 image, and is black or 0 or 1. So you can, so this one you just flatten into one long vector. Okay, so that's your x. Okay, so then each data is represented by a long vector x. So, but if you look at those numbers, because of the handwriting numbers, they could have a different variation, for example, for the 2, okay? So if you just look at it directly, they may not be well separated, okay? So you need to find a map, okay, a nonlinear map to separate those one, to make this more easily separate into 10 categories, for example. So now let's look at how this. So this is one example. This is not a deep neural network. It's just one layer. So you have some x. Okay. You after mapping, there's a linear mapping fully connected. Use the matrix. Okay. Then compose. Then there's an activation function. So this will keep something. You pass some threshold, then you keep it. Okay. And otherwise you drop it. So if it is, for example, below some threshold, you just put it in 0. That's a ReLU. ReLU do. So this is one simple layer. After that, you map to a function. So that's the simple example of a neural network. Now, for this example, I'm going to change the function. Now this is a scalar function, right? You can also use the vector function. It is reasonable. Now the output should be 10 digits, right? So your input is x. X is a 28 by 28 is a long vector. After that, the y is a vector of length 10. Okay, y is a vector of length 10. How do you compute this y hat? So this is y hat. You put this 10 vectors, and this w. This is a matrix. This is matrix times vector. Okay. So what is this matrix times vector doing? So A is transform the data, so not the original data. After that, you already learned some way to transform the data. After that, you also pick up 10 representative. So each category, you pick up a vector for those digits, okay? This is 0 to 9, right? So each category, each group, you pick up 1, it's called a theta I. So this is a vector in a high dimension, may not be in the original dimension. Okay, it could be in a high dimension, depending on how many neurons in each layer have. So those vector inner product of the vectors will measure the similarity of these two vectors. Okay, or if you treat this one as random variable, this will measure the covariance. Okay, so if you have some positive, so if this vector around the same direction, you do the dot product, you will give positive. If it is the opposite direction, then it's negative, right? So this tells you the similarity of this given a vector to this representative in each category. Now you take an exponential, then the negative one will, if the power is negative, exponential to negative, if more negative, then you're more close to zero, right? And if more positive, this exponential will amplify this this weight. So that's a nonlinear function. This is normalized. After that, the yi hat becomes a probability mass function. So the yi hat is a vector of length 10. Each component now is a number between 0 to 1. And what this number represents? It represents the probability of vector A in the category K. And the category or the group K is represented, you have a representation of theta. You do the dot product with theta, then you check this using those nonlinear mapping. This is called the softmax. Okay, so I also this is used a lot in this. So this one will change your result into probability density function, the mass function. This is also important. The mapping you obtain the hat is a probability mass function. Now, okay, here. So everything you have to change. This is not a deterministic. You give me a number, I won't tell you this number is 1 or 2. I only return you a vector with 10 components, tell you the probability of this number belong to. Okay, so because that's change point of view, okay, you can use this a very important concept called entropy for a random variable. That is the entropy. There's a probability mass function P, and you take some value of Ci with probability Pi. So what is the specific value of this random variable is doesn't matter. It only depends on the probability mass function, the Pi. So that's called the entropy. Okay. This Y without hat is something you want to know, is ground truth. Okay. You have the probability Pi, but what you can observe is hat is the approximation, and this one actually can change that. So Qi is the probability we just computed, okay, but Pi is something I don't know, okay. So the cross entropy, no, I should say, okay, so that's a two thing, okay. The unknown, the Y is something you want to approximate. You want to know, okay, this is unknown. That's correct. Let me return to this. So the cross entropy is you replace the entropy. Now this is a Pi, but now when this the ground truth is in the category Ci, but you only use this approximate one. So you have to take the log of Qi. The log is coming from this. You need how many digits to, you can, if you treat the base as 2, you need how many digits to represent this information. Okay, so that's something when you change to the probability point of view, okay, everything random variable, then you use the entropy, okay. This is a cross entropy between two probability mass function, and that's called a relative entropy. It's just the subtract constant. So when I say constant, because the variable is Q. Okay, so if you try to minimize the KL divergence or relative entropy, so you can easily prove this one will be a positive number, and this is equal to 0 if and only if P equals Q. So if you try to minimize this KL divergence, what you will really get is a true probability. Okay. So again, that's some background. So let's look at there's a M list. Okay, there's a digits. There's a line digits. So what is the loss function for each data? This is subtract the I. I is going from 1 to capital N. Capital N is the number of data. It could have 10,000 or meaning, okay, a lot of data. And for each data, you compute the cross entropy. Okay, this is just what we mentioned. Now the original one is just a scalar, right? You have a number you associate to 0 to 9, but you have to treat this scalar function as a vector in length 10. That means it's a probability mass function with some component is 1, other components are 0. If it is belong to K, it is 1. Okay, so that's a characteristic function. But now, after that, it is already changed to a vector. Then you can compare using the KL divergence for 2 probability mass function. So that's the cross entropy. Okay, now let's return to this. This is unknown. It means for a given new data you want to predict, that's unknown. But here you have some data which is called labeled data. So this is also other word terminology called supervised learning. You already have some data which you know the some information, future or label. That's the some you use those supervised or this labeled data to train your neural network, and hopefully given new data you can predict. Okay, so that's by using this cross entropy, sum over all the data points, you got a loss function, and this epsilon square term is called a regression. This is used added for the ease of optimization. Okay, so what you are going to do is doing an optimization problem. So what is the variable you can change? The variable you are going to change is the weight, is the bias. And this is not just one layer, you have so many layers. So you change your parameter, you change your mapping, change your y hat, right? When you change your y hat, you change your entropy. So everything depends on your parameter. Then you do optimization. Because of this capital M, this could be very large. So that's a popular optimization method called a stochastic gradient descent to solve this optimization problem. Find an optimum parameter, and then you got a deep neural network approximation of some nonlinear mapping. Okay, so after this mapping, then the 10 digits are well separated, and that's the reason you can use this for. Okay, in the old days when you deposit the check, you have to go to the bank, right? Now you can just deposit your check on your phone. I think that's due to those advancement of this deep neural network. For the numbers, this accuracy is amazing. Okay, it's approximated to 1, but level to 1. Okay, 100. So it's 99.99. Okay, very accurate. Now, as I mentioned, okay, this is machine learning, just using this some way to approximate your nonlinear mapping. Okay. So there are other choices. This is called a convolution neural network. So I have to skip some details. I use the first one, you understand the basic concept. So the convolution neural network. So originally you are two-dimensional image. Why you flatten into a long vector? If you flatten into long vector, you are going to skip some information in the 2D. So the convolution neural network mostly work on the images. So just take the two-dimensional image. You do two things. One is the convolution, okay? One is the pooling, okay? Of course, the nonlinear activation is also included, okay? That's the activation where you skip those those negative things, only keep those the positive single, okay? So that's the convolution, okay? That's the mathematical description of convolution, and capital F is called filter. And this things becomes more and more complicated. There's several filters, a lot of filters you can see from the picture. That's a stack of the images. Even the first one is just a single image. After that, there's several images, okay? Because of the filter you are using is different. May have a lot of filters. This is an example from the Go, okay? From the Go. This is the called call, okay? Anyway, so that's some pattern in the Go. You transform into a matrix, then you do the convolution. And after the convolution, if the sum is 0, that means that's going to be, then there's no such a pattern. If the sum Okay, if they have the same exact pattern, the sum will be a positive numbers, right? If more positive, this you check this. If the pattern is not correct, you have the 0 and the 1. The pattern not correct, then you got a 0, right? Okay. So the score after the convolution, they will tell you if this is a good indicator of the pattern. So you go through the whole board, then you can look for such pattern. Okay, that's the very simple example. And this pooling is reduce the size. You only keep 1. Okay, so what you are interested in is the pattern. So you don't have to. After this convolution, you may have a lot of zeros. You don't have to just record those zeros. That's one way to reduce the size. But anyway, I'm going to skip those details. Now, if you this is a convolution neural network for the M list, okay, recognize those digits, as I said, using those one is very accurate. Okay, so that's other things. Okay, oh, this is so after the convolution, then you extract the futures. Now the future, okay, those are some we call the black box. You don't know what the future looks like. Okay, you don't know. Okay, so that's learned by the algorithm. Okay, and you cannot actually look at the picture of the pictures is not meaningful. Okay, now this is a convolution neural network for the AlphaGo. Okay, so that's one important component for AlphaGo. They use convolution neural network to find the futures, find the patterns. That's the other important component called the Monte Carlo tree search. So that's the idea of this AlphaGo. They use a deep neural network. After several layers, after this deep, then you find some pattern which the human being cannot easily recognize. Okay, that's some deep futures. Okay. Now, as I mentioned, there's there's many architectures depend on your application. That's one more, for example, that's more relevant to our research. If your data, this XY, look at this, is a sequence. For example, there's a natural language process called the NLP. So the sentence, the input is a sentence. Each XI is a word. Okay. So that's a sequence of number of data. So this is a neural network designed for those sequence of data for NLP, the current neural network, okay, RNN. So each one, this one is a neural network. Okay. So the A here included some neural network I just showed you, but you have to pass to the next one. This is a sequence. So this is H is called a hidden state. So you are going to use the hidden state for the next one and the 2. So this will into the neural network of next one. So that's called RNN. Okay, that's the neural network for the NLP. Okay, for a sequence of data. But now for those data, that's an issue. It's called a long-term dependence. So because it's sequential, you can easily see this dependence, the dependence of the previous one can easily pass to the next one. But if you have some long-term dependence, just like you do a translation of some sentence, there's some words could depend on some word in a long away from that. Okay, that depend on the language you use. Okay, if you deal with a paragraph or article, there could be some keywords. There's a long-term dependence. So that could be an issue. That's the issue. Now, how to solve this one? There's a LSTM, there's other architectures to do that. Now, what I'm going to talk about is called this using those attention. Okay, here. So the idea is, so this is each word. Okay, you use RNN, then you get all the hidden state. The hidden state, you will use all the hidden state, not just one. Okay, not just one. Okay, let me show you the next picture. So this is a translation. So this is the input sequence. Okay, and this is the output. So you got the hidden state. Okay, so you don't use the original data. This is between here. There's a neural network. to transform the data. Now you have this two language. Now you are going to compute some correlation or similarity, form a matrix, okay? Because of the different language, they may have different order, okay? So so let's look at the next example. So this is a long sentence, longer. So usually you will see the diagonal that more relevant, okay, just one by one, right? But because of the language, they may have different grammar, okay? So you have to switch the order of the words. So you do see some off diagonal one, but still close to diagonal. But you may have some long-term dependence in the off diagonal, okay? Well, here comes this new, could be this state of art, this neural network architecture. It's called the transform. The transform, and this is based on the self-attention, okay? So what is the transform? This is a transformer. This in the classical sense, okay? If you search the transform, that's the optimum prime, okay? And the computer scientists, those are very good at choosing names, okay? So they call it transform. One way is you do transform the data, okay? Another one is show you this is so powerful, okay? Even powerful that this convolution neural network used for this AlphaGo. That's only AlphaGo uses CNN, okay? It's very powerful to find the pattern, but the transformer is even powerful, okay? Even more powerful. And they use this also Emo and BERT. This is some also popular name from this Salem Street, okay? Okay, so that's the transformer, okay? Now, the transformer that is even powerful. There's in this year, there's a breakthrough, okay, in this DeepMind, the same company who invented the AlphaGo. But the recent one, the shock the scientist is by the AlphaFold, okay? It's predicted the structure protein, okay? And previously they used CNN, and now they updated to the transformer. Then you increase the accuracy by 30%. I think it's just go also into the 90 this region. Okay, so that's a breakthrough. You see the alpha and the AlphaFold and AlphaFold 2. Okay, it's just updated the architecture of the neural network to transformer. Okay, so that shows how powerful this transformer is. Now let's look at a little bit of details of the transformer. So the original one is, this is an example for the translation. You give an input sequence and output sequence, and this is the black box. This is the neural network, okay? And this transformer, there's two components. One is called encoder, one is decoder. So encoder take the input data, doing some, this is a neural network here. That's some neural network here, and pass to the decoder, and also do some neural network. But in both encoder and the decoder, the most important component is called self-attention. Okay, self-attention. That's something I'm going to explain. Okay, so you are going to use some which we call the self-attention. That's the paper called "Attention is All You Need." Okay, it's published just a few years ago, but got a lot of citation. So that's something our research is on this one. Okay, self-attention. Let's look at what's this. So the attention, I already tell you, you just compute a matrix, right? Similarity. The self-attention is, I get the data. The capital X is a bunch of data. The N could be very large, a lot of data. Okay. Now, first of all, you do a fine map. This is the same as before, but now you have three. Okay. All those matrix W, capital W, are some matrix which is not known. You have to find it using the optimization algorithm. Okay. if your data is separable, if there's some structure, your this neural network that's doing optimization will find the parameter. Okay. So those are three metrics, and you do some multiplication, then you change it to KV. So that's called the self-attention. Is because you just work on this X, do a transformation, you got a three set of data, okay, but with different purpose. One is called the cure, one is called the key, one is called the value. So that's a picture, okay. So this is the input data. If you have a sequence of words, first of all, you have to change the word to a vector, embedding the word into a high dimension space, okay. That's called embedding. Now, after that, you become a vector. Then you multiply the matrix. You change it to different vectors. Okay, different vectors. They may not have the same length. Usually, the length could be shorter. Okay, but they have same bunch of data. Okay, so that's the other dimension. How many data you have, right? So you multiply the matrix. You still keep the how many rows you have, right? Now the next is you are doing the QK times Q times K transpose. What is that? This is a Q. This is a K, okay? This is a key, this is a Q. So each Q, this is a vector. You multiply by the K. So you are computing the similarity of those two vectors. But you have to go through for one Q, you have to put the dot product with all the keys. So it's like you compare to all the keys to see which one is more similar, right? So for one Q, you have to dot with all the Qs. How many? This is the number of data. Okay, the rows is the number of data. This could be very large, 10 million. Okay, for example, very large. Okay. Now, write in a matrix form is Q times K transpose. This will give you a matrix. But what is the size of the matrix? Okay. So that's the Q, that's the dimension of number of data times the K transpose. So the dimension of the matrix is capital N by capital N. That's like the similarities of the Q and the keys. And then you apply the softmax. That's something I mentioned before, okay? Softmax, you take a nonlinear map, or take the exponential and choose the maximum, okay? And the square root of D is a normalization. This is like a normalization. After that, this is like a computing the covariance. So this take a softmax and the V, the value, that's the also previous one. Then you got it. So you can think, you can simply write this one as A times V, okay? So although the A is nonlinear here, that's a softmax, is a nonlinear function. But essentially it's like a matrix times vector. So the issue is here. The issue is the A is an N by N matrix. So if you store the matrix, full matrix, you need an N square memory. When you compute the matrix times vector, you need an N square time. That's the bottleneck of the self-attention. There are a lot of work, recent work, very recent work to try to find a more efficient attention. Okay, more efficient attention. That's sparse, low rack, blah blah things. Okay, now we're going to talk about our contribution. We're going to use the first multiple methods to using some idea to develop some efficient and flexible attention. So again, you write this in an abstract way. This Q and Ki, Qi and Kj. You treat this one as particles. You are computing the interaction. As I mentioned, you think about the words. Okay, you are computing the relation of these words in a sentence. Okay, then it is reasonable to assume the dependent on the distance is the exponential decay. For example. This is geometry decay, by the way, depend on the distance. Then this is like they compute the gravity, okay? compute the gravity. If a far away, then this is less, right? Okay. So in the numerical computation or this computational math, we already have a lot of algorithms. Okay. The recent one, okay, the one I choose is called a Foster multiple. Now let me briefly mention the idea of the Foster multiple. So you want to compute the gravity of this X. This is a bunch of data, or you can think of particles. That's a one Y. Y is the curl. This is the keys. If you compute it directly, you have to compute one by one. But now, if it is very far away from this data, this particle, you can just treat all those small xi as one x star. You only compute once. Okay, so this, of course, is an approximation. It's not accurate. This is one calculation is approximation of the sum, but this calculation will be accurate if the distance between xi is much smaller than the distance between x and y. Okay, that's the okay. Before I talk about math, this is a picture to show you how to compute gravitation. You don't, when there's a galaxy far away us, when you compute the gravitation, you don't compute the gravitation to each star in the galaxy. Okay, you treat the whole galaxy as one, then you compute, right? That's the idea. Okay. Now, mathematically, that's mathematically it says. So the matrix, each entry is a smooth function of the distance, and they satisfy these properties. For example, this is gravitation field, okay? And it's called a well separated. If you can find a star representative, the inside of the group, the distance is much larger than the distance to the QI, to the targeted particle, the curl. Okay, the delta is a very small number, so that's just mathematically formulate. And after that, so this is a very simple example of using the Taylor series. So if you have such properties, the matrix and those data, then you can find a low-rank approximation of your matrix. Okay, so here the proof I'm going to skip. It's just doing the Taylor series. I take the 1D example. If you multi-D, you have to use a spherical harmonic. It's a little bit complicated. But a 1D is just a Taylor series. The ideal is just to replace Qi minus Kj by using this K star, using the Taylor series and the representative point. So what is the benefit of using the low rank structure? This is the matrix times vector. If you do if you store the whole matrix, is n squared. Sorry. If you do the matrix times vector directly, you are going to use n squared. But now your matrix, I'm going to replace by a low rank, for example, 3 vectors times 3 column vectors times 3 row vectors. So if you look at those 3, this is column vector times this row vectors, you still got an n squared matrix, right? But now when you multiply a vector, you can switch the ordering. You do the map to this product first and then to this one. So each one you only, not to the n, you only need a 3. So you reduce the computational complexity, also the memory from n squared to n. Okay, how many n is Rn, depending on the rack. So that's the idea of the Foster multiple actually. Now we combine this, using this, apply this to the attention. Okay. Recall that's the attention in this matrix. Now I'm going to use the diagonal, but not just the one diagonal. You can use several diagonals. That's like a 3, the K, that's the bandwidth. Okay. So you, for example, the K take a 3 or 5. Those are diagonals. And you still apply the softmax. This is one approximation. This is called the near field approximation. If the particle is nearby, you just compute the interaction directly. So this is an example of those. We take some attention matrix, okay, and computing the single value. You will see there's a decay, okay. But there's even more interesting is now you remove some diagonal, okay. This is the matrix we are showing. This is near field attention. I'm going to remove those diagonals and check the off diagonal, okay. So after you removing the diagonal, the off diagonal will be far field, will be weakly dependent. That's the low rack structure in the off diagonal. So this picture, this is an experiment to check, do we have this low rack structure for the off diagonals? So this is a random choosing attention, okay? That's a lot of data, so you will have a lot of attention matrix, okay? So you look at this. This is without removing the diagonal. So you will see the rack. The rack is this is a numerical rack of the matrix. This is a rack is around this 150. Okay, so that means basically you don't have this low rack structure. Okay, but after you remove the diagonal, 5 diagonal, then you will see the rack is more close to here, like 10. That means after remove the diagonal, 5 diagonals, then the off diagonal you can use the rack 10. After remove this 10 diagonals, then the off diagonal, since the rack is becomes within 10, okay? And after remove 20, it's like within 3. It's 1, 2, 3, 4, 5, okay, right? So that means after remove a band of diagonals, the off diagonal I can use low rack. That is the far field, I can use the low rack. So now the previous one is depends on the data are well separated. If the data is not well separated, but this is we already mentioned it before, you can map to a long high dimension space to make it separated. So that's called that's coupled with this nonlinear mapping. This phi, the future mapping. So you put all things together. That's what we call the FMMTransformer. So using the first multiple first multiple method and couple with transformer. Okay, you use this. This is the original attention, self-attention, use softmax and the full matrix product is n squared. Now you use some diagonal part and off diagonal part. Off diagonal is low rack, so you only choose R rack. And off diagonal, this you couple with the nonlinear mapping, okay? They make the data more separable. And if it is separable, then there's a guarantee of the low rack approximation, right? So that's the efficient attention we propose. That's also two parameters, W1 and W2. That's the weight in the combination of the of those two. Okay, those weight also can be learnable. So that means you can do further optimization and find a better weight. In some application, maybe W1 is more important. The diagonal is more important. So that's the mathematical formula, the attention we propose. Now we run, so the time is fast. So we run this one for several benchmark problems. And you will see, okay, those are different size of this sequence length, how long the sequence is. And you can see, this is the blue one is a softmax. You're using the gradient descent, it's converging very fast. Okay, and it's also cross entropy. That's something I defined before. This will reduce a lot. But this one is the original one is for the n squared. Now you replace by linear one. So that's the linear one is just replaced by 1, rack 1. That's some existing work in the literature. Now what we propose is you have to use low rack plus some, this is a far field, this is near field, okay? So you will see the improvement, okay? But the linear one, you can even, this is the rack, so you can also enhance the far field interaction with multi-kernels. That means increase the rack, not just the rack 1. You can use rack 2, or rack 3, okay? So that's also give you the improvement. Again, you cannot compete with the original one, okay? This is showing the computational time and the memory. So the red one, okay, this is original softmax. This is in the logo plot. So the slope is 2, so that's the quadratic. This one, the slope will becomes 1. That's the linear. Okay, that's to show you the when this length become larger and larger. Okay, this is the length. So for the large size, the capital N is larger and larger, then this linear complexity attention will win. Okay. Now this is also a benchmark long range arena. Okay. So you have a lot of after the transformer the self attention. There's a lot of this efficient attention proposed. Then in the last year, okay. So actually this is in the early of this year, okay, accepted in this early. So then the community propose some benchmark. Okay, you have a lot of new transformer or new attention. So which one is better? Then now the proposal this benchmark. You run those examples and show me the scores. Okay, then you know which one is better. Okay, so that's very interesting. Okay, so for some task, okay, not all the tasks, we even beat the original softmax. Okay, this is the original softmax. Okay, so this is the first one. The best score is in bold. Okay, so in some tasks we're number 1 even. Okay, and even this is number 2, but it's still far better than this linear transformation attention. Okay, they just use a simple rack 1. Okay, compose some kernel. Okay, this nonlinear mapping. We use this 2 kernel plus 5 diagonal. Okay, that's basically. Then you just even beat the original softmax. Okay, the performance. This one you lose just a little bit. Okay, this is either first one or second one. Okay, this is a very, and the complexity again is reduced to linear. Okay, there's another benchmark. Okay, so now this is like with experiment. Okay. So for this one, the softmax is still the best one. Okay. For this benchmark is the smaller the better. Okay. So for different benchmark, I have different criteria. The smaller the better. We're not the best one, but we are the second one. Okay, and close to the best one. This is the original softmax. Remember, you are going to use n square. Okay, so you sacrifice a little bit. Okay, you got a comparable performance with much less complexity. So that's the example using the fast multiple idea to develop efficient attention. There's a general trend is in the computational math, we have a lot of nice algorithms. Okay, we have done that. We are doing this for several years, way before those deep learning. We have a lot of algorithms. So we can borrow ideas in the computational math to the deep learning. Okay. Of course, you can do the other way around. You can also use some idea from deep learning to solve some problem in the computational math, mostly in high dimensional problems. Okay. So if we look at it this way, we can conclude our work is just simply apply the algorithm which is called the fast multiple in the computational math to the data science, to the deep learning, to develop efficient attention. Okay. Now, in this computational math for this low rack approximation, there's another algorithm. It's called the H matrix, hierarchical matrix, and you can. We just show a 2-level decomposition. You can do the multi-level to even further improve the performance. That's called a hierarchical matrix. And actually, the computer scientists, they follow this very quickly. They are doing those around we are doing the same time, okay? In this July, in the summer, they already did that, okay? They already did that. Okay, we are doing this also around May, like something like that. So this is like the future work, but just for a few months, they did it. They apply the hierarchical matrix to the transformer, okay? But there's a sequence of data in 1D, okay? And they also show this benchmark. They got a lot of improvement, okay? It's comparable to ours because they are doing the multi-level. They are slightly better, okay? There's another idea, which is called the Gallatin transformer. That's using this idea called the Gallatin approximation in this finite element to reinterpret this self-attention, this QKV, okay? In terms of this Gallatin approximation, and you remove this nonlinear mapping, this soft max, you rewriting this way, you can interpret this as a Gallatin approximation, okay? That's the work by Su Hao. You can also check. Again, those are two examples is using some ideas in the computational math applied to the deep learning. Okay, I will stop here. The time is also, I leave some time for questions. Any questions?
Thank you for the talk. Any question? If you have any question, please unmute yourself.
I'd like to say it was just an extraordinary lecture. Thank you.
Thank you. So there's a lot of what I want to propose is with this computational math, we have a lot of algorithms. Okay, we need to work on those deep learning things. If you have some simple idea, just but you have to do the programming. Okay, that's requires get some students or postdocs. Okay, you have to do some heavy computation. Okay.
So actually, I want to maybe ask some questions, but maybe not. I'm not an expert. I did not enter the field by now. The hierarchical matrix method, you mentioned the hierarchical matrix technique for machine learning. So what's the main part of that hierarchical matrix part can replace part of the machine learning? That's
no. The H matrix is a technical to compress your matrix. Again, your original one is you have a n square, right? So let me show you. Let me see if I can find a picture for this hierarchical matrix. I do have a picture for the hierarchical matrix. That's better to explain here. Can you see the screen? Oh, probably not in that one, right? So is that in your sharing? Can you see the screen?
It hasn't changed. It hasn't changed.
Oh, okay, I see. Let me do a new share. Okay, here. Let me stop sharing and share a new one. Okay, share screen.
Good.
Here. Now you see the screen right here.
yeah.
This is a typical hierarchical matrix. So in the off diagonal, this is a full block, but you can replace it by just one column times the vector, a row vector. So this part is essentially just 1n instead of n squared. Okay, so that's a compression. But this compression depends on the well-separated. So you have to decompose this hierarchical to a multi-level decomposition. And this one, you can use rack 1. But now you have to do this decomposition again, okay? And using the rack here. So that's called a
Okay.
herodic. What I just talk is just the 2 level, diagonal plus low rank.
Okay.
But now the herodic is more complicated. It's like this. Okay. And the coding is, or the programming is also complicated. But those Google researching, those they have time, okay, and they are also very good at this implementation. Okay, so the herodic matrix, that's the herodic matrix. It works.
Okay. Thank you. So another question is about maybe for the low rank approximation. What is the best R you choose? Depend on the benchmark, which benchmark you are testing on. So what is the R you are selecting? 3 or 4 or whatever. It's depend on the benchmark, right?
That's a good question. So what are your where's my here? Okay, so the benchmark here. Okay, it all depends. Okay, so we also have this. Remember, this also have a weight. W1, W2. So you have to train for different benchmark. So all those, this 5 now is, I will just choose some 5, but this 5, this linear mapping also depends on benchmark. So that's the low general rules to have one parameter for all the benchmarks. So usually it all depends. So that's like doing experiment, okay? You have some idea, philosophically it works, but what is specific value, then you have to depend on the data, depend on the benchmark, depend on the problem. Is that answer your question? Or?
Yes, yes. And another question from Tanzang, and they make the comments, ask a question about how to map the original data to high dimension. Does it mean if the original data is m dimension and we add n dimension feature to help to separate data, then we need to find the n dimension curve to separate them?
That's something I didn't. So that's the dimension. If then this is actually, so if this is the input data, that's like the length of the vector. Now that's the number of neuron. Let's call the neuron. That's the map of the data. That's the length of the vectors. You could be larger. You also could be smaller. Okay, it all depends. What the dimension you use also depends. You could use the original dimension or also increase the dimension. Usually that's a low universal rules. Okay, here. So how large the dimension are, I don't know. Okay. So how do I say that? You don't have to worry about this. Okay, if you're not large enough, add more neuron. Okay, add more to that. So the one thing is you add more neuron. That's the length of the vector, or add the layers. Add more layers. That's also somehow this is head waving. This is like an experiment. Yeah. When you do more, you have some experiments. What is the layer you choose? How many layers you choose? How many neurons you use? And you don't have to worry about how to find the separation lines or curves. So it's all encoded in this weight W. And the algorithm, you're doing this optimization algorithm. You have some loss function, then you just use optimization. You change this weight to minimum some loss function. This procedure will find the optimal weight for you. You don't have to. So that's they always say this is a black box. You even don't know what is the map that the future this is. Like the CNN, right? They extract them some future, but the human being cannot understand it.
Yeah, I have one question.
Yes.
Yeah, Dr. Chen. Yeah, thank you very much for your very well-organized introduction and your new approaches. So in your softmax that layer, do you have any energy or wise relevancy? Energy gives energy, the kind of free energy base. Yeah.
That's a good question. Okay, so here this is like a more statistical. They use the cross entropy. So entropy, this word you can also find in the physics. So I don't know, but there could be some relation to those energy. You can treat this loss function using the cross entropy as kind of energy. You are minimize some energy. That could be, but I'm not so sure about the exact correspondence between this. But this could have some relation between the cross entropy and some energy in the physics. But now this is more from the statistical point of view.
Actually, when the energy is conserved, there is more relatively simpler case. But when you consider correlation, covariance, and interwoven connectivity on those ensemble of particles interaction, then it's definitely more complicated. Yeah. So energy and entropy definitely goes together. Yeah. Thank you.
Thank you. So any more questions?
Yeah, I'd like to add another comment. I want to say, I thought I said it before, I thought it was a beautiful lecture. I especially appreciated the early introduction where you really started from the beginning. That's an ideal lecture beyond the beautiful work that followed it. Thank you.
Oh, thank you. So that's because I think our math community. We should. I want to introduce some this basic idea about the machine learning to the math community. So the idea is pretty simple. This, if you understand it, that's just a combination of those linear map plus the nonlinear activation function. But that's a very powerful representation. That's some magic. So I think the deep learning, okay, philosophically speaking, is they provide a new field for our mathematician. We should look at those problems. There's many problems there. Okay. So the computer scientists mostly they like the algorithms, like implementation, like this engineering. They make those works. But why? That's I think that's the job of this mathematician. We need to understand why. Still, there's a lot of things going on. Now, what I did is just a description, still not a deep reason. Why this compose this deep neural network, you can capture those deep futures. This is, we don't know. And I think our mathematicians should work on this to this is like a new problem. Like they go back to the Newton, they find the problems from physics, right? Now there's AI, there's deep learning. This is like the old time, the physics in the old time. Now we need a new Newton, like find the laws, first the principle laws, to understand those black box. The AI is doing amazing jobs in many fields, right? But still there's a lot of research to be done. Okay.
But I think that calling it artificial intelligence is exactly wrong. I mean, it's kind of, it's a black box, it's total ignorance. There's no logic in it. I mean, you do the computation until it goes over and over again. So calling it intelligence is logic and reasoning, and it's just the opposite. It's a strange name. Artificial, except for, unless you emphasize the artificial.
Yeah, that's yeah. That's the artificial. So that's philosophically okay. Again, that's another. So the intelligence now it's like a computation. From the pure computation, you can have the intelligence. That's something seems weird. Okay.
Thank you for the discussion, and thank you for the comments. Yes, it's important to our math community to embrace such a cutting edge and popular topic, and have a better and a deeper understanding of deep learning. So, I really appreciate Dr. Chen to give us such an excellent talk. And it did increase all the interest of both Morgan and other universities, researchers, and students interested in this field. So I noticed that there are many external audience. Some are actually from China, some actually from Europe. I realized. I should say that I'm sorry that because of technical restriction, some want to attend this talk, but I do not know how to change the setting of the meeting. So some of them could not attend this talk. It's a pity. But anyway, I already made the record of this video record of this meeting. So in future, if some of your friends want to have the video, just let me know. Or maybe I should put in YouTube or other online website. Anyway, I thank Dr. Chen to give us talk, and I thank all of the audience attendance. Thank you for your participation. Looking forward to some make comments. Okay, Phil was said Happy New Year. Yeah, Happy New Year to everybody. Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Okay, let me end the talk. We have around 5 or 6 participants from Morgan, and other around 15 from all over the world. So next time, maybe I will also invite and post the room link, and then send the link to maybe in WeChat, maybe in maybe even Facebook. So we may have more audience. All right. Okay. Happy New Year. Okay. Bye-bye.
Bye.